All right, hey everyone, welcome back. So we're gonna talk a little bit right now about polynomial regression. So kind of what that is, when we would use it, and how we would interpret some coefficients that would result from fitting a model using this polynomial regression. And so polynomial regression has a couple of uses. I think the most obvious use is that it can help with nonlinearity issues. And so you might remember for your car project in particular, many of you, though not all of you because it depended on the car model that you ended up choosing, but many of you had this kind of price versus age or price versus mileage graph that kind of looked something like this and had this very nonlinear pattern where the car's price depreciated a lot at first, but then it kind of flattens out over time as the car gets older and older, or as the car accumulates more and more miles. It could also help with prediction. And so we kind of know how to use models to make predictions, but we haven't really talked about this as a goal explicitly yet. And so we'll see that actually in the very next note packet. We'll focus a little bit more on prediction. And so what this model is it's just going to expand our usual simple linear regression model with just the slope and intercept. And it can add some extra terms. So it could add a squared term, a cubic term, to the fourth, to the fifth, to the sixth, to the seventh, to the eighth. Not quite as high as you could go, but as high as there are a number of observations in your data set, you could go up to that point. Usually the most common thing to do is to just do the quadratic is, I think, by far the most common, or cubic. But it depends on the level of nonlinearity that you observe in your actual data. And so the common examples of this are the linear model. So this is just our simple linear regression model. We already kind of know what that is. The quadratic model with our predictor squared term in there, and a cubic model. All right, so that's kind of when we would use this polynomial regression, some very common forms of it. I guess we're going to kind of take a second to talk about what exactly we mean by a linear model. And so this class really just has to do with linear models the entire way through. But so far we've kind of assumed that we know exactly what a linear model means and what models fall under that. But it could be a little bit confusing, I think, or less than intuitive, that models like this quadratic model still count as linear. And so linear models are anything that are linear within, or that are additive in the beta coefficients. So if the beta coefficients kind of appear like this and are in some kind of weirder spot, then the model qualifies as linear, at least the way most people use that word in stats. And so like a multiple regression model with a couple of predictors, that's still a linear model, even when we talked about transformations. It doesn't matter that it's not linear in x, it's still linear in the beta coefficients, and so this still qualifies as a linear model. Nonlinear models are somewhat rare to see, but a couple of examples might be something like this. Or something like that. And so something where you aren't adding a beta coefficient times some other term to your model. This beta coefficient is in the denominator, this one is in the exponent, and so these would qualify as nonlinear models, which we will not talk about in this class. And in my personal experience, I've rarely ever used a nonlinear model. All right, so the last thing we are going to talk about with quadratic regression before kind of jumping into an example on R is how to interpret these regression coefficients, as well as can we interpret these regression coefficients. And so the coefficient that we actually can still interpret if we aren't extrapolating is the intercept coefficient. So we could still say that when x is 0, we expect the average response to be beta hat naught units. All right, so that's kind of easy enough to interpret. It has the same interpretation as the intercept in simple linear regression, so that's kind of easy enough. Our beta hat 1, so just to be really clear, we're talking about a model in the quadratic regression context, so something like this. So our beta hat 1, we can't interpret that, and beta hat 2, I guess I'll say in our usual way, we can't interpret it, and we can't interpret beta hat 2 either, though you might know from calculus, if you've taken that, that beta hat 2 still indicates concavity. All right, so you should be able to kind of transfer, if you've taken calculus, I know not everyone necessarily has, but if you have, you should be able to see why beta hat 2 still would indicate concavity, because this is just a quadratic equation. And so intuitively, we can't interpret beta hat 1, and you could take a second to think about what's wrong with our usual interpretation. So why can't we say, as x increases by 1 unit, we expect the average value of y to either increase or decrease by beta hat 1 units, as long as the other predictors in the model do not change. That would be how we would usually interpret a slope coefficient in a non-quadratic model. But we can't actually do that here. And it has to do with this last part that just doesn't really make sense. And so the idea is that we can't increase x by 1 and then say x squared doesn't change. So this interpretation just contradicts itself and just doesn't make any sense. We can't say as x increases by 1 unit, blah, 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 as long as x squared doesn't change, because if x goes up by 1, then x squared just has to change by definition. Okay, in the R example that we'll see, we'll kind of compare a quadratic regression approach to an approach involving indicator variables with a categorical predictor instead. And we'll kind of see some benefits and drawbacks of each approach looking at this SAT data example.